Okay, how's everyone doing today? This is Mike Johnston here, and I am going to bring you a little video and show you the proof of how to determine the quotient rule of derivatives using the definition of the derivative via limit. Many times as we advance through calculus courses, we often just apply rules without actually knowing why we do it or without actually knowing why the rules work the way they do. So this video is going to be used in order to show you how the quotient rule came about and the reason why we're able to use the quotient rule the way that we do. First of all, let us go ahead and remind ourselves the definition of the derivative using the limit definition. So this will be the limit as h approaches 0 of some generic function f of x plus h minus f of x all over h. And this right here is the limit definition of the derivative. And this is a generic function f of x, and we assume that f of x is differentiable, and that is one of the biggest assumptions that we have here, is that it has to be differentiable and that it's not equal to 0. And by doing so, we can apply the limit definition in order to determine the derivative. However, let us assume, so we're going to have to make some assumptions here, that we have two functions, f of x and g of x, are functions that are differentiable. And by us saying differentiable, we know that f prime of x and g prime of x exist. And we're going to state that g of x will not be equal to 0. So this will be an important assumption that we have to state before we can go ahead and apply any of our calculus to find the derivative of a function that is rational or that contains a function divided by another function. So let us go ahead and define h of x. Let us go ahead and define h of x. Okay, let us go ahead and define h of x. Well, we're going to say h of x will be equal to f of x divided by g sub x. And notice here the reason why we said g of x is not equal to 0 because, excuse me, if g of x did equal to 0, we would not be able to find the derivative of h of x. So now in order for us to find h prime of x, we will have to use the limit definition of the derivative. So let's go ahead and work this through just like such. So applying our limit definition, we will have the limit as h approaches 0, f of x plus h divided by g of x plus h. So everywhere we see an x, we're going to plug in an x plus h, and we're going to have to do it both for our numerator and our denominator. We have to subtract our original function, which will be f of x divided by g of x, and this will all be divided by a value of h. Okay, we can now simplify these two, and again, these two are just fractions that contain functions. In order for us to subtract fractions, we have to have common denominators, and here we can recognize that our common denominator will be g of x plus h times g of x, so we will still have the limit as h approaches 0. I'm going to multiply by 1 over h here, and we will have f of x plus h all over g of x plus h. But we're going to multiply by g of x on the bottom, but if we do so on the bottom, we're also going to have to do so on the top. And then we're going to subtract. This is a subtraction. This will be f of x, and we're going to multiply by g of x plus h on the numerator. That way we can multiply by g of x plus h in the denominator. Okay, then we can all fit it in there. So now since we have common denominators, we can go ahead and subtract our numerators. So I will rewrite this as the limit as h approaches 0. I'm going to keep my 1 over h out in front, and I will have f of x plus h, g of x, f of x plus h times g of x minus f of x, g of x plus h. And this will all be over our common denominator of g of x plus h times g of x. Okay, so all we did here was subtract two fractions with a common denominator of g of x plus h times g of x. I'm going to go ahead, I'm going to work continuously down the page instead of trying to squeeze this all in on the right. So at this point we recognize that we have an f of x plus h, we have a g of x here, we have an f of x, and we have a g of x plus h. So hopefully we're recognizing the definition of that derivative to always start with a f of x plus h, g of x plus h, whatever our function's name is, f, g, h, whatever it is, it doesn't matter, subtracted by our original function all over a value of h. So notice here we have a value of f of x plus h, and we have a g of x. The trick is, we are going to have a trick, and the trick here in this circumstance is that we are going to subtract out an f of x, g of x, and then we're going to add in an f of x, g of x. So we're going to subtract f of x, g of x, and then we're going to add f of x, g of x. And notice if we subtract f of x, g of x, and we add f of x, g of x, we are still adding a value of 0, and that is not violating any mathematical rules that we have. But we're going to do so in such a fashion that ultimately we're going to be able to find some derivatives. So let's go down here to the next slide and see what we have. I'll let us all see that. So we will have, this will be equal to the limit as h approaches 0 of 1 over h, this will stay here. We will have f of x plus h, g of x. I'm going to subtract out f of x, g of x. And then I'm going to add in f of x, g of x. And I still subtract f of x and g of x plus h all over g of x plus h times g of x. So we still have a fraction. All we did was subtract f of x, g of x and add f of x, g of x. And by doing so, we are not changing our original problem. We haven't violated any constraints. But now let's go ahead and split this up. I'm going to split this up. I'm going to distribute my 1 over h and my limit because we know the limit of the sum of two functions is the sum of two functions will be the limit of each function summed together. So here I will say I have the limit as h approaches 0, and I'm going to split these up right down the middle here. So I'm going to show you where I'm going to split them up. I'm going to split them up right down the middle there. Common denominator will be g of x plus h times g of x. Okay, so we are going to have f of x plus h, g of x, minus f of x, g of x. This will all be all over. The h will distribute in here, so we're going to have h times g of x plus h times g of x. So I'm just splitting this up, and we are going to then add the limit. We're distributing the limit of h approaching 0 as h approaches 0. And here we're going to have f of x, g of x, minus f of x, g of x plus h, still all divided over. This h must be distributed to this fraction as well. So we're going to have that 1 over h here, still times g of x plus h times g of x. So notice here we have a common factor or common function. We will call that common function g of x, and we can pull that g of x out here. And notice over here, if we're trying to form the derivative, we would need this g of x plus h to come before our functional value of g of x, noticing we have a common function of f of x and f of x here. So we're going to have to switch these two terms around, making sure to watch out that negative is attached to f of x and g of x plus h. So in my next step, I'm going to go ahead and I'm going to factor out the g of x in my first limit. So I will have the limit as h approaches 0, and I will have g of x times, now I'm going to write this in blue so we can all write this in green so we can all see that we're going to be left with f of x plus h, and that f of x plus h is coming from here, and we're going to subtract out f of x. We're going to subtract out f of x, which is this guy right here, and I'm going to close off my set of brackets. And notice over here we are still going to divide out. I'm going to pull my g of x out to the front so we can all see how ultimately this g of x will cancel. And we are going to be left with h times g of x plus h. So we're going to have h times g of x plus h. Okay, so we're going to be left in such a fashion to have g of x plus h still times g of x. So all this is here. Hopefully now we recognize that g of x is going to cancel out. And now we're going to add, noticing here, I'm going to bring this to the front. So I'm going to have the limit as h approaches 0. I'm going to have minus f of x, g of x plus h. And I'm still going to have plus f of x times g of x. And this is still going to all be over h times g of x plus h, still times a function of g of x. So in order for us to substantiate and apply the definition of the derivative, this negative would have to exist between g of x plus h and g of x. It would be g of x plus h minus g of x all over h. So what I'm going to do in our next step is that I'm not only going to factor out a function of f of x, but I'm going to factor out a function negative f of x. So in this circumstance, since we are taking the limit as h of x approaches 0, g of x, our function of g, is actually just a constant. And we recognize that we are allowed to cancel any constant that exists. So in this circumstance, I will continue. We will have the limit as h approaches 0, and I'm going to pull this g of x plus h out to the front. So I'm going to have 1 over g of x plus h. This will all be times f of x plus h minus f of x all over our value of h. So hopefully we're recognizing now the limit as h approaches 0 of f of x plus h minus f of x all over h. I hope you all see now this is just f prime of x. And here I'm going to factor out a negative, so this sign will go from plus to a minus. And since f of x is just a constant, because we are taking the limit as h approaches 0, f of x is a constant function, I'm going to pull out that f of x. So I will have f of x. Notice I will be left with g of x plus h. So I'll do this one in red so we can all see where it comes from. I will have g of x. I thought I was going to do it in red. G of x plus h. And I pulled out the f of x here, and we'll still have now a negative turns to a, positive turns to a negative. So I'm going to have minus g of x. And that g of x comes from there. And notice here, we can still all be left over the functional value of h, which I'm going to put here. We still have g of x plus h times g of x. So we still have g of x plus h. I just rearranged this. So hopefully now we are seeing here that we have just a value of f prime of x. And hopefully now we see here that this is just a value of g prime of x. That is just a value of g prime of x. So you have to be careful here about the notation, because this by definition is f prime of x. So what we're going to do now is that I'm actually going to go ahead and I'm going to take the limit as h approaches 0. So as we take the limit as h approaches 0, I'll do that here in blue. I'll do this here in blue. So we realize this h will go to 0. We realize this h will go to 0. This is just f prime of x, and this is just g prime of x. So let us see what we are left with after we go ahead and apply our limit. So noticing here, we will have 1 over g of x, and that came because the h approximated 0 as we took the limit. And notice this is just going to be times f prime of x. This value is just times f prime of x. We are going to subtract out this next portion. We're going to have an f of x still on top. We have an f of x still on top. On the bottom, we're going to have g of x, this approach 0, times g of x. G of x times g of x will give us a value of g of x, quantity squared, because we have 2 g of x's. And over here, this portion all went to g prime of x. This portion all went to g prime of x. So hopefully now we're seeing how the derivative of our function that we called h of x at the beginning is formulating this quotient rule. So now we're just going to be left with some simple algebra. Notice our common denominator, we're going to subtract two fractions. We have a g of x here. We have a g of x squared here. We're going to have to multiply through by another value of g of x here. So in our numerator, we are going to have g of x times f prime of x all over. I had my original g of x, but I had to multiply through by another g of x. I won't want to combine too many steps here to confuse anyone. So now I'm going to have still nothing changed over here because we have that common denominator, which is the function of g of x squared. So we're going to have f of x times g prime of x all over g of x quantity squared. Hopefully now we can recognize that we have a common denominator of g of x quantity squared. Therefore, since we have a common denominator, we can go ahead and subtract our numerators. This will equal to g of x f prime of x minus f of x all over g prime of x all over a common denominator of g of x quantity squared. And this, ladies and gentlemen, by definition, is the quotient rule of our original function h of x, which equal to f of x all over g of x. That right there is the quotient rule. And I know there is a little saying that a lot of my students have used in the past, and they say low d high minus high d low. They say low d high. So they say low d high minus high d low all over the low squared. The low squared, this just says low g of x, our bottom function, g of x, derivative of high, derivative of our top function, d high, minus high, which is our top function, the numerator function, over the times the derivative of the denominator, which is d low, derivative of g of x, which would be g prime of x, all over low squared. So this is how we are able to prove our quotient rule using the original definition of the derivative, given that you have that function of f of x divided by the function of g of x. I hope you guys found this video informative. If I can ever answer any questions, please let me know. Thank you.